if we think of agriculture as management of plants, which it is, what we've shown, and I think I'll just draw a quick thing about grass. You have to remind me of time. I have no sense
I will.
of time.
I'll let you know.
This is what's happened here. We started looking at our grass on this ranch, and when I began the project in 2007, I actually did not know the difference between an annual plant and a perennial plant. My background is construction. I was a union carpenter and then a construction project manager. It turns out that grass is a pretty interesting thing. A perennial grass plant actually has a tremendous root system. Perennial plants allocate a tremendous amount of their carbon and their energy to develop roots so that they can get access to water and nutrients in the soils. Annual plants really put all their energy into above-ground biomass production to make seeds, very simple, shallow roots. They grow, they die, they dry. So on Earth right now, we actually have seen a shift to an annually dominated system through human management over the last 200 years. So on Earth right now, in rangeland systems, what we're seeing is a system that is fairly short-lived, and because of a couple of events, warming temperatures and out-of-season rain events, grassland systems, which are part of rangelands, the single largest cover type on Earth, have become a source of emissions. So what we used to think of as a global carbon sink has now become a source of greenhouse gas emissions. The grass plants grow, they die, they dry, rain events happen, they rot. That's a greenhouse gas source. The soil system is wetted, the soil microorganisms get activated, they're hungry. So they start eating carbon out of the soil in the humus and the occluded light fraction. So we are now priming the system to become more and more and more of a source of greenhouse gas emissions. What we're looking at is perhaps is there another way of managing our grass system, and we started working with Jeff Creek using grazing management as a tool to promote these native grass plants. And so the native perennials, and we have green plants in this yard right here you could look at. These little plants can be 300 to 500 years old and have 9-foot deep roots. That's a complete different story than this guy here.
Wow.
That means that when the fog happens, whatever time of year, the plant can continue to perform photosynthesis. So rather than an annual plant which has a 2 or 3 month long window of photosynthesis, we now have something that can keep growing year round, getting deeper, deeper, deeper roots. It can also tolerate droughts and things like that. So our grazing management under Jeff's direction was to bring the animals in before these went to seed, eat them, which allowed sunlight to get to the growth crowns of the perennial plants. And we've got about 20% coverage of perennials now in this system by grazing management alone. So what Jeff was suggesting, that what we're probably seeing was increases of soil carbon, and that this success that we were enjoying was a result of carbon in the soil. This was getting interesting now. The soil was starting to feel more and more spongy, and more success we had with this. And we had the opportunity to meet with Dr. Wendy Silver, a UC Berkeley biogeochemist. She knows everything about the soil system, and she's an atmosphere soil gas exchange scientist. So we met with her in December of 2007 at the Lawrence Berkeley lab and asked her the question, is my management of my grass system increasing soil carbon? She said, I doubt it, and I doubt we can measure it. Jeff said, I think we're actually doing it. He'd been measuring at McAvoy soil organic matter, half of which is carbon, increases. And what numbers were you saying there from grazing and compost?
Well, doubling it.
Doubling it.
Soil organic matter.
So half of soil organic matter is carbon. He'd been measuring that increase in his systems. Wendy's saying, I doubt we could measure it, I doubt we could see it, and I doubt you're doing it. So there was a very important lesson that I had at that point. She said, if you're talking about soil carbon, you need to know it's much more interesting than just bulk soil carbon. It's actually on a continuum, very temporary to permanent. Most soil carbon is labile. Most soil carbon is in the bodies of microorganisms and plants. Most soil carbon is going to respire to the atmosphere through those living organisms, and that's the global signature that we see for microorganism respiration. So most soil carbon is temporary, going to the atmosphere, restoring the resource base from which plants grow. However, just as a matter of circumstance, it could be in the surface of the soil or a meter deep, some carbon is not in the bodies. It may be the dead body or the waste product of microorganisms. And this is now physically protected. This is the occluded light fraction. This is soil carbon now that it's sticky, and it actually causes good soil structure, PEDs. And when that happens, it changes the electrical properties of the soil, and water that was subject to gravity passing through the system now becomes detained in a particulate form, which is a plant available water. So increases of soil carbon automatically increase the water holding capacity. And then just as a matter of circumstance, also some of carbon ends up chemically bonded inside microsites within the soil structure. This could be the waste product or the dead body of a microorganism permanently inside a little structure. This is heavy fraction carbon. This will last for the millennia, or for millennia, however you say that, unless you plow. When you plow, you break that structure, microorganisms get access to that carbon, their waste product are plant available nutrients. So we see a biomass response when we plow. It looks like a good thing, but we're burning up our fossil carbon when we do that. So our question to Dr. Silver is, are we increasing soil carbon in the two more recalcitrant fractions through a land management practice? She said, I doubt it, I doubt we can measure it. Jeff says, I think we are. Based on this background, we said, well, we need to know what our baseline level is if we're going to compare a treatment and see if we have results. So we conducted a survey of 35 sites in Marin and Sonoma in 2008 from January to June. These are dairy pasture and beef pastures, and we measured, we discarded all the labile carbon and measured the heavy fraction carbons and the occluded light fraction carbon. And we found something amazing that surprised even Dr. Silver. We found 30 to 120 tons of carbon per hectare, and a hectare is 2.5 acres. And I've seen different numbers, but this is basically around the idea here. This is a big spread. Dr. Silver said, what happened here? Those sites had all had wet dairy manure sprayed on them to dispose of it. The ranchers do that to get rid of the manure. They also see a long-term biomass response. It makes more grass growth. There's a tremendous amount of methane and nitrous oxide emissions from doing this. So any carbon increases probably are not a net benefit, but it showed the scientists that a topical application of an organic amendment resulted in permanent carbon increases. Very exciting discovery. And then Dr. Silver did something really important. She sent that soil to have it carbon dated. In 1996, the French deployed a nuclear device that released a discrete carbon isotope into the atmosphere globally. Dr. Silver said, I was looking for a needle in the haystack. She found bricks of carbon. This is 10-year-old carbon we found 1 meter deep in Marin County soils in a permanent form. How did that happen? This is amazing. So what we saw and measured was recent air, carbon in the air, photosynthetically had come through plants and ended up in a permanent form in the soil system. So we designed a set of experiments on this ranch and in the Sierras to test this idea. And it was Jeff's idea to use compost rather than manure. So we randomly assigned treatment and control plots on this ranch and in the Sierras up in the research-owned extension center there. And rather than manure, we're going to put out compost, which is a biologically stable carbon-nitrogen complex. And it was Jeff's suggestion that we put 1/2 inch out. So prior to the application of compost, we conducted a complete biogeochemical analysis of the soil. UC Davis conducted a above-ground biomass mapping. We knew what plants, where they were, and how many. We knew everything about the compost. And starting earlier in 2008, we started using an infrared gas analyzer to measure soil system respiration. So we basically had the boundaries defined around this. On December 8th, 2008, we put 1/2 inch of compost. Prior to that, I should have mentioned we installed full-time sensors measuring soil moisture and soil temperature. On December 8th on this ranch, December 12th in the Sierras, we put 1/2 inch of compost at one time. And then by May, each of us had completed our grazing cycle. So we had different soil, different grass, different grazing management, different climate. The same exact compost was all both directions. And by May, we went back in and looked at the results. We saw, and it's a range, 30 to 70% more forage production, which was very exciting. And it turns out, now that we've measured or seen the data, it's a more nutritious grass, it's higher protein. We measured 26,000 liters more water per hectare, having the full-time data measurement, 24/7, more water compared to the control. And then for our purposes, very exciting, we measured 2,000 pounds of carbon molecules that came in per hectare. And so by priming the system one time with a topical application of a biologically stable carbon-nitrogen complex, we've ignited a state change. And how that expressed itself was the second year with no further compost, another ton came in on its own. That was amazing. And then the next year, and the next year, and the next year. We're on our 6th year now. Every year with no further compost, a ton of carbon is coming into the system. The computer model in Colorado State, I love hearing wow. It's pretty good.
Yeah, it's
The
pretty
computer
good.
model shows this will go for 30 years, if not 100, from a single application of compost.
Wow.
Now the grazing only side lost carbon. So grazing alone will not do it. And you can think of it as a bearing with no oil on it. The more you use it, the worse it'll get. Our systems are degraded. They've lost their carbon. One little drop of oil on the bearing, it'll start moving smoothly. That's what we've done. We put a little bit of carbon. The system now is actually moving smoothly.